6.5 is called compound inequalities. So we are going back to the number line type inequalities because I believe section 6.3 and 6.4 we were doing the kind of inequalities where it had like an x and a y variable, and that sort of just meant you would like be graphing in the xy plane. But so here we're going back to like the number line inequalities, and essentially the word compound means that there's going to be two at once. And so here in this example we have this inequality where there's only one variable, and the variable could be x, it could be y, it could be m, it could be n, it could be q, like whatever. I suppose most of the time it's going to be an x variable, but don't get thrown off too much by the y variable. It could be an x, usually it could be an m, it could be a b, whatever. So all we're really going to do is graph both of these on the same number line, and they're separated by the word or here. Alrighty, so this one on the left, 4y minus 2 is greater than or equal to 14. Just like you've done a million times, we're going to solve for the variable, and this should be nothing new, and then we must divide both sides by 4, and we would not flip the inequality symbol here. It's not like we were dividing by -4, so it stays greater than or equal to, and it ends up being y is greater than or equal to 4. Over here, likewise, we're going to, work on getting the variable by itself. -13 plus 4 should be -9. Once again, we're not going to flip the symbol, and I'll just kind of bring the word or down. And so our final answer, before we graph our final answer, because usually the graph is a part of the final answer, or in a way like the graph is the final answer, but our final answer in a way is y is greater than or equal to 4, or y is less than or equal to -3. And all we're really going to do here is graph both of these on the same number line. So for this one, y is greater than or equal to 4. That's going to be a closed colored in circle on 4, and everything to the right of 4. So greater than or equal to 4, or less than or equal to -3. So less than or equal to, so we -3, so we color in the -3. And that's the final answer for, as far as the graph goes. That's the final answer. Now, to start to try to give like a little bit of like big picture context. If you have two separate inequalities connected by the word or, this is almost always what the final graph is going to look like. Your two graphs going in opposite directions. Like this one's going in this direction, this one's going in the opposite direction. That is almost always what's going to happen when the word is or. If you have a compound inequality, the word that is being used to connect the two inequalities could be the word or it could be the word and. Okay? And those words really mean everything as far as what the final answer is. So allow me to elaborate a little bit more here before moving on to the next example. Let's say you were starting a club, you know, an exclusive club where you either had to be, like you had to be a part of the club, you had to be, let's say, a student at Fort LaBeouf, or you had to be a girl, right? So in order to get in, you had to be a student at LaBeouf or a girl. Now think about that. What does that mean? The fact that it was the word "or" that was used. Would the boys in your class be included? Would your mother be included? You know, I mean, all you had to be was like one or the other. You know, you didn't have to be both. You know, if you were any girl in the world, you could be in the club. You know, because the word was "or." If the word was "and," if you had to be a student at Fort LaBeouf and a girl, then you got to fulfill both requirements. You know, and so anyway, hopefully that helped a little bit. But when you translate it to here, the overall solutions are greater than or equal to 4 or less than -3. All of these are good. All of these are good because it's if you're here or if you're here, you're good. So when the word is "or," you pretty much include everything in your final answer. Because if you're here, you're good. If you're here, you're good. Like you're automatically a part of the final answer. And so the entire both graphs, sorry about the bad grammar there, but you know, are good. But anyway, once again, when the word is "or," usually the problem is going to be designed to where this is what your final graph looks like anyway. It's not 100% of the time, but if you see the word "or," you can pretty much, it's a pretty safe bet that your final graph is going to look like the two graphs here running away from each other. The next example, finally, we have two separate inequalities, but now the word connecting them is "and," which, if you think about that social club example, is a much stronger word. You know, it's like it's got to be this and this. You know, like a double requirement, and you got to fulfill both of them. Anyway, but for the most part, it's going to be like the same deal, where you're just going to solve each inequality separately, like you've done a million times. And so you get 3x alone, and then -27 plus 1 is, or well, I'm getting ahead of myself there, huh? -28 plus 1 is -27. And then, of course, we have to finish getting x all by itself by dividing both sides by 3. And so we got x is greater than -9. Over here, we're going to be subtracting 7 and then dividing both sides by 2. So, and again, the word here is "and," okay? We have to be greater than -9 and less than 6 at the same time. So, oh man. Looks like my number line needs to, right? -9, okay, is off in that direction, and so, but here I can just say, 5 and 6. Plot twist. Number line needs fixed a little bit. Oh well. Okay? Anywho, getting back to the main idea here. What's our final graph going to look like when we're only supposed to be graphing numbers that are greater than -9 and less than 6? It's got to be both of these because the word is and. That's just the way the word and works. So, let's kind of build to the final graph, I guess. Everything greater than -9, goes in that direction. Everything less than 6 goes in this direction. But I mean, you take this graph, for example. This graph on its own, just this on its own, this goes forever to the left, So numbers that are less than 6 include like -10, -11, -12, -13, -14. But you don't want this graph to actually keep going past here because, you only want to be graphing numbers that are not only less than 6, but are also greater than -9. So we're not going to want to include on our graph like the -10, -11, -12. Likewise, numbers that are just greater than -9 include numbers over here like 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. But we don't want this graph to keep going to the right forever either, because once again, it's both of these together. And so what happens here is you let these graphs come together and connect with each other, and you only want to end up graphing everything in between -9 and 6. So on that, to end it here, just like I sort of said about how almost every time when you have the word or, this is what the final graph is going to look like. The two graphs going away from each other, But on that note, if the word is and, you can pretty much expect your graphs to be going into each other, and it'd be like an in-between type graph. Okay? The graphs going towards each other and colliding together. Okay? Now, the third and final example, this is another compound inequality. There are two inequalities here. They're just smooshed together like this. And if you were to separate them into two, separate inequalities, it would be these two inequalities, and, well, no pun intended. And the word connecting the two separate inequalities would be the word and. So when you see something like this, the word behind the scenes is the word and, It's two inequalities connected by the word and. So what that basically means is we can expect the final graph to look like this, the two graphs going into each other, colliding. Now we can solve both of these separate, just like we did in this example, right? Solve here for x separately, solve this for x separately. That would be fine. But I'm going to show you a different, just a slightly different approach, like a little twist on it. I can just get x by itself in the middle of this, smooshed inequality. I can just get x by itself in the middle. I'll start by subtracting 3 from the middle, the right, and the left. And so that's going to make it -8. It's going to leave 2x alone in the middle, and then 9 minus 3 is 6. But we still have to divide by 2, middle, left, and right, to get x all by itself. And you should recognize something like this, where it's just x in the middle, as everything in between -4 and 3, with an open circle on -4 because of the symbol, and a closed circle on -3 because of this symbol. And so again, it's a smushed together graph, because what this sort of says is x is greater than -4, but at the same time less than or equal to 3. And so at the end of the day, it's just everything in between -4 and +3, including 3, but not including -4. And that's the basic gist of section 6.5. Again, there's more to this whole story. Like I kind of said, when the word is or, you can pretty much expect the graphs to be going away from each other. When the word is and, which includes situations like this, you can expect the graphs to be going into each other and colliding and having like an in-between two numbers type graph. But even though it's going to be like that like 99.9% of the time, you can have like some crazy situations happening and some different scenarios happening, you know what I mean? But we're not going to so much focus, especially when it comes to like homework and tests in this integrated math 1 class. When you take algebra 1, you're undoubtedly gonna see all different kinds of different examples and what you should do and how to handle all different kinds of curveballs and things thrown at you. But for now, for this class, an AND graph is going to pretty much look like this, and an OR graph is pretty much going to look like this.